Hey everybody, welcome back to Young Engineers of Today. Hope you had a good weekend, and I hope it was pretty interesting. Anybody do anything cool? Maybe, hopefully. Well, at any rate, hopefully it was a relaxing Easter weekend. Um, it's good to have the time off from school and all that stuff. And well, I can't remember. It's been a long time since I've been in high school. Uh, is Easter weekend actually like? Do you get the day off on Monday? Well, whatever. Um, at any rate, we are going to continue with Eagle. Yeah, Eagle. It's exciting and full of all kinds of stuff. Yeah. Let me go ahead and get that opened. So once we open Eagle, this should look pretty familiar to everybody. You've got the documentation, the libraries, and the design rules, all that kind of stuff. All this stuff should have remained the same from the last time you used it. So just like last time, we aren't going to have to go back in and reselect all the libraries we want and all that stuff. Nor is it really going to be an issue right now because we've already gotten all of the components down that we need to, and so the our schematic is more or less done except for all the connections. So let's go ahead and open up YEOT board schematic. And look at that. What is this? A schematic for ants. I'm going to go ahead and maximize it. There we go. So here's our sort of layout of all of our stuff with some connections made, not a whole lot. We made all the ground connections because for some reason that was the thing I insisted that we do by the end of class. I just wanted to get some of those done, all of those done before it was time to go. I actually don't think I got all of the grounds that we needed, but whatever. We'll figure it out. At any rate, it should look something similar to this. We've got sort of a liberal sprinkling of components here and there, and some of them are connected. As I said, the barrel plug up here, the power jack, is connected to the power on the ground, as well as a capacitor. And I spent some time sort of wandering off on a tangent about capacitors, and how they're essentially batteries that discharge more quickly, charge more quickly, and don't tend to hold as much. That's just kind of how they are. However, it does kind of, in this sense, like a capacitor here for an Arduino, what that's meant to do is that's meant to equalize the power draw. So when you're getting power from a plug in your house or something like that, it's not necessarily guaranteed that that power is going to be always level. In essence, I know I'm getting off on another tangent here, but I find this stuff kind of interesting, and I explain it to you in the hopes that maybe you'll find it interesting too. Anyway, in your house, you receive power through the outlets in something called alternating current, as opposed to direct current. Direct current is just the electricity goes through the loop, the electrons all move in one direction, and it's pretty straightforward. Alternating current, the electrons actually kind of wiggle back and forth. And if we were to look at like maybe a graph of power over time for like direct current, you might have something like this with, maybe the implied sort of wiggling because it's not going to be constant necessarily. However, with alternating current, things get a little wacky. This up here, this line is 0. The line is 0 here. And the graph looks something like that. So it actually kind of dips down below the 0. And that's not to say you're receiving negative power. Like, you're not, you know, your house is not powering the electric grid. That's not what's going on. This is actually more a measurement of current. So in essence, what's going on is, the electrons move forward, they kind of wiggle backwards, they move forward, they kind of wiggle backwards. So there is, hence alternating current. The current can dip into the negatives. If a particular appliance is built for that, that's fantastic. If not, that's a problem. Really big problem. Which is why you have, like, wall bricks and stuff like that, because your phone is the battery on your phone or on your laptop or on your 3DS or on your whatever is going to be a direct current circuit. That battery just supplies current in one direction. It needs to get recharged using an alternating current circuit. So that's why you have those big ugly wall bricks, or they call them wall warts or whatever, power bricks. Those transform alternating current into direct current so that it's compatible with your direct current device. Anyway, tangent of a tangent. Point being, the reason why we have, 120 volt alternating current is it's actually the average. At any given time, if you were to measure the voltage coming out, certainly the current coming out, it's not going to be exactly as advertised. However, the average over time is going to be 120 volts, and usually, I can't remember. I want to say it's 2 amps? Maybe? Potentially? I don't know how high my voice can go. But I can't remember off the top of my head right now. Regardless, because of so many variables between conditions at the power plants, to the lines that bring it to your house, to the transformers, to the lines that are in your house, to the connections between, the wall plug and the wall outlet and the plug, and the quality of the wires, and just so many other things, you're not really necessarily going to get 120 volts constantly. You're not going to get, the average in amps constantly. Same thing with direct current, just because physics. These things happen, so you're not going to get a constant output, which means that anything plugged into it is not going to get a constant input. So that's what a capacitor does. A capacitor equalizes everything. It means that it'll take a little bit longer to turn on, usually on the order of milliseconds after you plug it in, before it actually gets enough power to turn on. But while it is on, it will experience a much steadier power input, which is good for the device. Variable power input, like if things start wiggling around, like you start getting variable voltage and stuff like that, that's not always good for the life of the device, especially when you have microcontrollers, which depend upon a constant power input. So that's the point of the capacitor right there. And in many places, the capacitor's on inside of the IC, on the circuit, things like that. A lot of times that is the point of a capacitor, is to sort of equalize that power graph, I suppose. The power over time, the voltage and the amperage over time. So that it extends the life of the circuit. Things act, with... So you can with more predictability, more regularity, because especially with things like with integrated circuits and power on or computing on computers and stuff like that, because those kinds of things Like when you think about a computer and how it runs in all binary, either a transistor's on or a transistor's off, well, they're not going to be dealing with simply, digital electrical input. It's not going to be binary. They could be, receiving half a voltage, they could be receiving 2 volts, they could be receiving 5 volts on that circuit. However, there is a cutoff on a transistor as to whether or not it's considered on or off. So like say at 3/4 of a volt, anything 3/4 of a volt and above, that transistor is considered to be receiving power and on. It's a 1. Anything below that, it's a 0. If you start getting variable, power draw, suddenly, let's say you hit a low point in your power draw, well, something that would be right on the edge there, receiving that 3/4 of a volt, will suddenly dip below it and will consider itself to be off, and vice versa for on. Something right below that 3/4 of a volt in a little bit of a power surge, well, everything equalizes out over the circuit, so it will receive more and it will be considered on when it's supposed to be off, and then weird things will happen. So with like a microcontroller, you especially want to be sure that your power is consistent. Anyway, that's this kind of stuff. I think it's kind of crazy how we've managed to take electricity and turn it into a computing machine, like literally, and then we've managed to take computing machines and turn them into basically an inextricable part of our lives. We're all living with really, really, really super duper fancy calculators. Calculators that can do all kinds of stuff. Calculators that can call people, that can play games, that can, do your taxes for you, although that one's kind of a given. That can store thousands and thousands of files of information on whatever, that can show you cat videos, like calculators. We just have, like, that's where the name computer comes from. It computes. We just take that output, we take those computations, and we turn them into stuff that's more meaningful for us in our day-to-day life. We said, like, oh, hey, what if when a 5 comes out, it's the color green, and we put that on the screen, and somebody was like, hey, what if we did that for like every single pixel on the screen, and then, cat videos. Anyway, that's why I got off on that tangent. Let's continue with the actual lesson, since we haven't done a single thing yet. Haha! Basically what we're doing right now is we're just connecting everything together so that we have actual useful representative connections on our schematic. We know what's supposed to be connected to what else. Once we know that, our lives are going to be a lot easier when we're working on the PCB side, because Eagle will be able to extrapolate that just like 123D Circuit did, and show us all of the stuff and give us those little green symbolic connections telling us what should be connected to what else, which we can then do the copper trace and all that stuff like we did with 123D Circuit. At its most basic level, this is a very similar thing to 123D Circuit. We create the schematic, we connect all the stuff in the schematic, and then we go over into the board view and we lay everything out and connect all the stuff there. It's just this has a lot more going into it. So yeah. What shall we connect next? Well, let's connect up our VCCs. Let's just do the obvious thing here and connect up all of our VCCs. Remember, when you actually want to make connections in Eagle Circuit, there are 2 options. You've got bus and you've got net, and we want to use net. Net is the only one that Eagle counts as sort of like a valid connection. Bus exists for kind of representing connections if you want to make sure everything works before you put it out there, and then various things like that. But we want to use net when we're sure that the thing we want to connect to the other thing is actually the things that we want to connect. Eloquently put, I know, but let's do that. So let me go ahead and click net over here, and then I'm just going to connect this resistor to this power up here. Why here? I don't know. I just picked one arbitrarily. There's no real, necessary order that we have to go in. As long as everything's connected the way it should be, that is good enough. So I'm going to start at R4, and I'm going to connect to VCC, and bam. Should be pretty familiar at this point. It's all coming back to you now. This is exactly what we were doing. last Wednesday. And I know it's incredibly exciting, but it's something we're going to want to, do. All right, and I'm actually going to spend some time moving this stuff up a little bit in order to make my life easier, and you'll see why in a moment. If your stuff was largely around this pin 1, then you're fine. No need to worry about it. Mine wasn't, so I'm moving everything up to give myself a little bit more room. Because I'm going to go back down here to nets, and I'm going to connect C2 to pin 1 on this microcontroller, this PC6/reset. And then I'm going to connect R4 to that connection. Connect. So that's what we have right here. We have power going into the resets. We have a capacitor here. Presumably this is like a little reset button or a reset pin. We wiggle something around in order to reset the microcontroller and bring it back to, basically status 0, like nothing's going on. And then we're going to take this VCC, VCC, and we're going to connect it down here to, actually we're going to do that the other way around. We're going to take pin 7 here on the microcontroller, and we're going to connect it up to VCC. And then we're going to take a VCC and connect it to that connection. Now, again, to reiterate, you'll notice that there are dots here, there's no dot here. This is one of the standard things that's done with schematics. A dot means that these two things are connected. So pin 20 is on the same line as pin 7. R4 is on the same line as C2. No dot means they are not connected. So you can think of it like a three-dimensional space. So this connection here with 20 and 7 is either running below or above this connection here with C2 and R4. Regardless, it's not touching. Another way that tends to be represented in schematics is like with a little jump. So you get here, and then there'd be like a little jump here. And that means the same thing as this lack of dot here. It just means that those two are not connected. The jump is, I like to use a combination of the jump and the dots because it helps me to sort of separate things visually. But when you have a lot of connections, a lot of times it can get visually messy with having a ton of jumps like that, and more modern circuit schematics don't tend to have the jumps. They just tend to have nothing there to signify no connection. So, personal preference, but you guys, if you ever get into this kind of stuff, you're going to be seeing a lot of this as opposed to the old school kind of jumps. I'm going to come down here to our AVR, SPI, PRG 6PTH. I know it's a mouthful. I'm going to connect this +5 to the VCC, because +5 is just another way of saying VCC. It's another way of saying a plus. It's really, there are a million ways to express power in the connection sense, and that's just one of them. And that's one of the annoying things about circuitry, schematics, circuit design, things like that, is there isn't really a standardized way to represent all of these things. There are like 3 standards for ground, and there are like 4 standards for VCC. And it's just one of those things where you got to get used to the different standards in order to know what you're looking at. Anyway, I'm going to connect this VCC to pin 8 here. Generally, it's better to start with the lower pin because of the elbow. I mean, again, it's all personal preference, but I like to have the elbow bending in at the last second like that. It looks neater. Not in like a radical dude kind of way, but in like a neat and tidy kind of way. And it's just easier to read. But with that, we've actually connected all of our power and grounds. We could basically have this circuit, well, at the very least, we could hook it up to power and have there be a complete circuit. But we're going to do more than that. we're going to actually have this circuit do interesting stuff, because interesting is always better than boring, right? Anyway, see this stack of pins right here, 23 through 28, and then this stack of pins here, 7 through 2. We're just going to connect them one to one. Super straightforward. Just like that. 23 to 7, 24 to 6, 25 to 5, 26 to 4, 27 to 3, and 28 to 2. That's strange. Oh, it's not strange. I'm just dumb. Okay, I thought the numbers lined up oddly, but they didn't. They don't. So that's what we have. Now we've fully connected J2 to our ATmega 328P underscore PDIP. I'm sorry, I'm just enjoying saying the full name right now. So now, let's go ahead and connect our J4. No, let's connect our LEDs. Let's connect our LEDs. First things first, though, I'm going to have to move the LEDs down because I am a poor planner, and my computer's yelling at me. Okay, so I'm just going to drag these down one by one, like so. Give ourselves a little bit of room to work with. And there we go. And the reason for that is because these LEDs and these grounds are going to be hooked up to pins 14, 15, and 16 here. Just these are going to be outputs, and they're also going to be hooked up to LEDs so that we can get status. Basically, these are little status pins, which relate to various statuses of the microcontroller, whether reset or on or whatever. That's what these LEDs are for. These LEDs are meant to be helpful status LEDs, so that we know what the ATmega is doing when it's not hooked up to a computer and sending information into it. So we'll net these. So now D1 is hooked up to pin 16, D2 is hooked up to pin 15, and D3 is hooked up to pin 14. Like so. Now we're going to get J4 hooked up. And by that I meant J3 because I misread it. But it's going to be an interesting thing. It's going to be a little bit different from how we normally do it. So what we're going to do is we're going to create some nets off of this that don't go anywhere. So you can just click outwards and then hit escape to bring yourself out of the net tool so that you can draw another one. So there we go. We've got 6 nets that just don't really go anywhere. Why would we ever do this? Well, do you remember the representative or symbolic connections that we had in 123D circuit? Like when we made that screw terminal block, hooked it up to a power and ground, and then gave those power and grounds the same name as the power and grounds on the other part of the schematic. And they were meant to represent literally the same connection, like the same thing. Like they were not just connected to each other, but they represented the same item. So what we're going to do is we're going to basically do the same thing here. We're just going to give them names as opposed to representative symbols. So now what we need to do is we need to find the name tool. Text. No. Let's go up to draw. No. Name. Okay. So it's going to be under the edit menu. It's going to be name. You can also see over here in the toolbar, it's got the R2 over 10K. If you mouse over it, it says name. The one next to it is value. We want to make sure we're giving it a name. So we're going to click on name, and then we're going to click on this net right here. And it'll pop up with new name, $14. Really not useful. We're going to call it G&D.
Warning.
Yes, we're going to connect $14 and G&D. See, this is exactly what it's asking us. It's asking us if we want to connect this net right here to the ground, because we gave it the same name, which is exactly what we want to do. So we're going to say yes. And it should have popped up with a name. Okay, well, whatever. We know it's named ground. Next, we're going to do that with this one. We're going to call it CTS. Hit OK. Boom, done. Next, we're going to do this one. VCC. It's going to ask us again, do we want to connect it to VCC? Yes, we do. Are you sensing a trend here? We're going to name these things the same thing that is on the actual device itself, or the representation itself. So this one's going to be TXO. This one's going to be RXI. And this one's going to be DTR. So now that we've named all of those, excellent. Now they're going off into the representative connections. They don't necessarily represent anything yet. Then they're going to, go off into a sort of a via an open place that we can plug stuff into. Anyway, that allows us to create a more complex circuit while still looking simple. Because, I mean, it doesn't look any more complex than it did before. It's just, it's just got these 6 wires off of there. If the names were properly showing, then of course we would see the names, but they're not, so we can't. Unless, let's see here. Show, nope, layer settings. Names. Well, whatever. They're just not showing up for some reason. Anyway, we're going to do the same thing down here with this little monstrosity. The AVR, SPI, blah, blah, blah. And it's going to be the same kind of deal. These are going to be, we're just going to net them out. Net, net, net. And we're going to give them the same name as what they're connected to on here. So this is going to be MOSI, MISO, SCK, and reset. RESC. Nope, doesn't have the same number of letters. Thought you could do it to the tune of respect, because, I'm a dork. Anyway, we're almost done with all of our connections. We have to connect this capacitor up here to something, right? Because it can't just be sort of like a dangling capacitor. That doesn't make any sense. So what are we going to connect it to? Well, we're going to take advantage of our naming. So we're going to net out on C2, hit escape, and we're going to name this net DTR. I just wanted to remember that. So we're going to call it DTR. It's going to ask us if we want to connect the two. Yes, we do. So now, because this is DTR, our DTR down here is technically connected to the capacitor up here. And then we've got this one connected to ground, and then power. And we've got a CTS and TXO and RXI that aren't accounted for yet, but those will get, fixed. If not now, then in the circuit design. But for all intents and purposes, our circuit's looking pretty dang good right now. I'm going to close out my... What are we naming the last one? Oh, you mean the one hooked up to the capacitor up here? That one's going to be DTR. So that essentially we have a connection running to this DTR right here. Is that the one you meant? Okay, cool. Just want to make sure. Excellent. Excellent. All right, so we do. Yeah, we definitely do have a few more connections to do. So first off, I'll be the first to admit this. I made a mistake. I'm sorry. But we can get this fixed. So let's go back over here to J4. Got a little overzealous. Actually, we're concerned about these two right here, TXO and RXI. So that's going to be transmitting out and receiving in. That's what TXO and RXI are for. We actually just want it to be TX and RX, respectively. So under the name for TXO, the net for it, just change it to TX, and under the name for RXI, on that net, just change the name to RX. So now we should have TXO connected to the net, which is labeled TX, and then RXI, which is connected to the net labeled RX. The reason for that is because we're going to connect them to over this area over here, RXD and TXD. So once you've got those renamed, go ahead and draw a couple of nets to nowhere out here. And then for RXD, you're going to name it RX. It's going to ask you if you want to connect it. Yes, you do. And then under TXD, you're going to name it TX. It's going to ask you if you want to connect it. And yes, you do. Now we've got this MOSI, MISO, and SCK. Let's go over the AT mega real quick. Hey, would you look at that? MOSI, MISO, and SCK. So, one might reasonably assume that we're going to want to get those connected to one another. We'll do that the same exact way. Let me zoom out a little bit, give myself a little bit more room. Nets, nothing but nets. I'm so sorry. And then MOSI. Yes, we want to connect it. MISO. How many? Sorry, what do you mean? How many are we doing? Like how many connections are being made here? Oh, sorry. Yeah, okay. So we just did 2 and 3. And then I just did 3 more down here at 17, 18, and 19. And as you can see, the names here line up with the names that we've got on this little doodad right here. So what we're going to do is just name them. So like this net right here has this name, and then this net right here has this name, and then this net right here has this name. And that's all. So far, we got a couple more things we're going to do, but we're nearing completion of the schematic here. So I'll give everybody a moment to do that, and then we will move on. Oh, 2 and 3 were named TX and RX. Let me go ahead and bring that back up. Clear erase all drawings, bring that up. So 2 was RX and 3 was TX. Just like what we have right here. All right, no problem. Of course. Okay, so, oops, there we go. Cancel. All right, we've got one more up here. We've got the PC6 and then the slash reset. And we've got a reset down here. We're actually going to make this a reset wire as well. So we're just going to go ahead and straight up name this net reset. Morning. And that's it. Just go ahead and click on this net right here, name it reset, and then now this net is connected into it. And with that, everything should be connected to everything else on the schematic in some form or another. Which is fantastic. That is, that means we're ready to move on to the board part. With an A, not an E. Hopefully. Hopefully you guys aren't, bored. Oh, puns are horrible. Puns are horrible. Homonyms will be the death of me. Okay, anyway. So now that we've gotten everything connected to one another, now it's time to actually move over into board mode. Bum, bum, bum. So, how do we go about doing that, you might ask? Well then, I've forgotten. I'll be honest with you. Okay. If we go up to, is it File? Yeah, okay. So if we go up to File, there's this little icon here, and then there's this command switch to board. We're going to want to click on that. Boarding. And it's going to say the board blah 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 does not exist. Create from schematic. Yeah, we want to create it from the schematic. Otherwise, we're just going to have an empty board, and that's going to be really boring. It's going to be not exciting. So I'm going to click yes, and it's going to think, and look at that mess. Look at this mess. Look at it. But we've got some things here. So this, and they've got names on them, so it makes it easier. Here's our power jack, our barrel plug. Here's that AVR thing that we've got over here. Here are our LEDs. So that's these right here. That's what these are. We've got some jumpers. Here's our J2 jumper. There it is right there. Here's our J4 jumper. Here it is right here. We've got our 3 resistors. Remember the resistors that are hooked up to the LEDs. And then we've got a 4th resistor, which remember shoots off from the reset pin to power. And then we've got a few capacitors hiding. Oh, there they are. Geez, right in plain sight. We got a couple of capacitors here too. This big honking thing down here, this is the AT Mega. This the main event right here in the middle. It's meant to represent an AT Mega integrated circuit. So it is going to be roughly the same size and shape as an AT Mega circuit. AT Mega 328 IC. So, all in all, we have all of our stuff here, including we've got our released under the Creative Commons attribution, share alike, blah, blah, blah. But if we wanted to, we could click on Move up here, and we could start just, dragging the stuff onto our board. That's what I'm going to do right now without any real regard to where anything is oriented or placed, just so we have everything on the board. Also, fantastically, it's probably going to be easier to see on your screen than it is on mine. You can see we've got a whole lot. Oh my goodness. Thank you. Please stop saying, you have to be very precise about where you click it. Otherwise, it's just going to blonk at you, or in my case, say the word caution over and over again, because that never gets old. Again, this was designed by and for engineers, and user interface was not really first priority. It should be said, though, this will make your life easier. So this area with the cross here, there's a cross on each of these components. That's where you want to click in order to be able to move it. That's how Eagle can be sure that that's what you want to move. Because again, there could be 100 bajillion things on this board, and you want to be exactly sure about which thing you're clicking on. So you remember how small resistors are from the picture? Now resistors can be larger, they can even be smaller. They're generally larger if they're, resisting a huge amount, or if they're put into a circuit which is going to have a lot of current going through it or whatever. But generally they're roughly the same size. So this should give you an idea of how large everything else is on this circuit. That is to say, not very big at all. Not very big at all. We've got some pretty small jumper sets. We've got some pretty small barrel plug. Well, it's a regular size barrel plug, but it looks ginormous compared to everything else. We've got a pretty small jumper set, a different jumper set as opposed to jumper cables. And we've got the AT Mega itself is pretty tiny too. But let's spend some time trying to orient this. So again, we take up a small amount of space because we could spread everything out, but we don't necessarily have to. And the same maxim follows from before. A smaller board is a cheaper board. So let's go ahead and just spend a couple of minutes trying to arrange everything in sort of an optimal position. Now, there's not necessarily going to be any right answer, so you can orient it however you like. You don't need to follow how I'm doing it on the screen. I'm going to kind of be stumbling my way through this, to be perfectly honest. Okay, so you can right-click to rotate things as you're dragging them. Just as a side note, let's see here. I really wish that they had different color connection lines, because that would make it a lot easier to see what I'm doing. Wonder if there is... There we go. So if you want to make your life easier, you can go up here to Options, and then User Interface, and under Layout you can set the background to black, and it will be a lot easier to see the connections. A lot easier.
Caution. Forcing pilot eject.
Okay. Yeah, also, in a bit of a departure from 123D Circuit's interface, if you try and bring something outside of the board on Eagle, it will actually just not let you do it at all. With 123D Circuit, it will allow you to do it, but then it will pop up with a thing saying, hey, this shouldn't be here, which, gives you an opportunity to kind of fix your mistake and, slap your forehead and move on. With this one, though, it's going to say that it's not going to be able to do it at all. Strangely enough, specifically because it is the free version of Eagle. I don't know. Maybe in the paid version of Eagle you can put stuff outside of the board temporarily. Some jumper cables off to the side, or jumper connections. Bring this capacitor up here. Bring this set of jumpers over here. Rotate. Rotate. That looks better. Put our status LEDs alongside underneath it. Again, there is no particular right or wrong answer. You guys feel free to connect this however you so choose.
Caution.
Just going to do that. Okay, so I've got everything more or less arranged how I would like it to be arranged. More or less. It's not amazing. I'm not exactly an arrangement pro, but it'll do the trick. It's this whole bird's nest of connections here. We're going to fix that. But first, what we're going to do is we're going to shrink the size of the board. So if I just click and drag one of these walls on the board, it dutifully draws in. Also, don't be me and grab one of the corners, because it's just going to be a pain to make sure all the lines are straight again. Not too bad, but, kind of annoying. Anyway, this is our, well, my final board design. Your guys' is probably going to look different. Just kidding, it's not our final board design. We have to connect everything still. But this is how the layout looks. So at the very least, when we get started with this on Monday, we'll start making all of our connections. We'll hopefully finalize the design. That can be a pretty time-consuming process, just because there are a lot of connections here, and we're gonna have to figure out how to connect everything so that nothing overlaps. However, the same deal that was in 123D circuit exists here, and that is there are two layers to this PCB. So we can exploit both a top and a bottom layer in order to ensure that stuff doesn't touch when it shouldn't touch. Just like how maybe you don't like having your eggs touch the pancakes because then they get syrup all over them. We want to make sure that stuff doesn't touch that shouldn't touch, because then that creates a short circuit, and then everybody's day is ruined. You spend all this time building a circuit and you plug it in and then it catches fire. And, I mean, it's kind of cool to have like a fire maker, but it's a really expensive and time-consuming fire maker when they make matches for that kind of a thing. But regardless, that's what we're going to spend time sort of puzzling out on Monday. I will also say that there is an autocomplete mode in this that will automatically create the connections for you. It's not strictly amazing, though. It has sometimes problems. But whatever. Regardless, that's not the point anyway. We're going to spend the time creating our connections manually, because it's more interesting that way. It's more like a challenge. So with that, I'm going to ask the poll questions. I know it's a little bit early, but it's just there isn't really a way to gracefully segue into the next bit without taking another 10 minutes. A, because I'm a fairly talkative person, and B, just because I want to make sure that we get all this stuff introduced before we actually start creating connections. So I'm going to ask the poll questions, and then we're going to leave it open to question and answer time, and then we will break for the weekend, because it was a pretty easy week, only one class this week. Anyway,